share the screen. And I'm going to open up the document. All right, so as I said, these are the notes. And really what I'm going to do is go through regression modeling, basically. Okay, so as you know, we had your homework assignment for the wine quality data set, right? You tried multiple deep learning, machine learning algorithms with PyTorch, and then you also tried random forest, and you also tried XGBoost. I actually don't have a description of random forest here, but this is more general for regression trees in general, and leading up to XGBoost, which is kind of the state of the art. I also have the papers here linked, so I should be able to point them out for you guys. Okay. So basically, I'm going to start a description of just why it's important, what regression is, and then we're going to talk about regression trees, kind of the basic idea of regression trees, and then historically some of the important ones like AdaBoost. I think some of you may have looked at AdaBoost, and then we have Gradient Boost, which I think someone actually tried, right? Gradient Boost, and then we have XGBoost here, which is the final one, in contrast to neural networks, basically. Okay. So the idea with regression is, as you guys know, let's go over here. So in statistics and machine learning, the question of how well a model performs for the data is sometimes described in terms of bias and the variance trade-off. Okay, so this is really the idea. So how well can we fit the data using the train set, and then how well the model generalizes to the test, right? So that's really the intuition. So as you have basically done in your experiments, you train on a train set a model, and then you applied it to a test set, basically. We know that certain models, like linear model, linear regression, right, will not overfit, but they may not be able to capture the structure of the data. On the other end, we have things like neural networks, right, which we know can fit really well to the training data, but we just don't know if if they can generalize well to the test set, right? And that's usually called overfitting. Regression trees are able to fit nonlinear data like neural networks, basically. Okay, so basically here we're talking about linear regression trees, and also neural networks. So we know neural networks are really good, but as you have found out in your experiments, regression trees were better, right? So that's really then the focus of today's discussion is just, some of the main ideas of regression trees, basically. Okay, so regression trees can fit nonlinear data. Regression trees are a type of decision tree in which the predicted values are not discrete classes, but are instead real valued numbers, okay? The key concept here is to use the features from the samples to build a tree. So you can imagine a tree that we are building, which is going to be made up of nodes. And so you're going to have decision nodes, and you're going to have leaf nodes. Usually the decision nodes are basically decision points that you have in the tree, right, to decide, okay, do you go to the left, do you go to the right? And then that gets you to leaf nodes at the end, which will have values that you can use to calculate your final regression value, okay? So that's basically the idea, okay? So as this states, the key concept here is to use the features from the samples to build a tree. The nodes in the tree are decision points that lead to leaves, and the leaves contain values that are used to determine the final predicted regression value. So the question is, how is this done? Okay, so I'm not going to go into all the specifics of the algorithms, but kind of just try to give you an overall idea. So for example, if a selected feature, let's say just one feature, ranges from 0 to 255, like in an image, then a threshold value such as 115 can be selected to decide which child node of the parent node should be moved to, okay? Once the selected feature's threshold is established, this cutoff is used to help select the output regression value. And that's really what we're trying to do, right? So we're trying to select the features, and then once we've selected the features, we try to select the threshold values. But that can be, anything, right? So from 0 to 255, how do we know that it should be 115? Why not 114 or 113? Do you see that? So that's the basic idea. So in the simplest case, the child node on the left can accumulate all the output values that correspond to the values below the threshold for the given feature. Concurrently, the right node collects those above the threshold. And then simply averaging values in each node can provide an initial predicted value, right? So that's basically the idea. However, this method is not the best solution, right? So just doing that is not the best solution. So the goal in training regression trees is to try multiple thresholds and select the ones that provide the best results, okay? And this is done through an iterative process or iterative optimization, and comparison of predicted values to real values is how you find the optimal solution. Do you see that? So basically, it's very similar to what we do with other techniques, right? At the end of the day, we end up with something like this, where for each, you can think of it as having a tree candidate, right? So you have 3 regression candidates, all right? And so each one of these is going to predict the value, and then you just compare those predicted values to the real values. Calculate the difference, and that's going to give you basically a type of error. So at the end of the day, this is the goal, the basic optimization goal that you're trying to achieve. Does that make sense, guys? And this is the basic intuition of regression trees. Okay. So as this states, through iterative optimization and comparison of predicted values to real values, optimal regression trees can be obtained. So the algorithms are there focused on that process. Okay. So regression trees start from the top and work their way down to the leaf nodes. And leaf nodes are used to select output values. So that's usually where you're in the process of training the model. You're trying to decide cutoffs of features that are optimal, and then also the values that should be in these leaf nodes, basically. And that's the algorithm. So non-leaf nodes are typically decision nodes that are based on the optimal threshold of the range of values in that feature. So the key question is how to select which optimal features to use and how to determine the optimal threshold value for a given node. That's really, in all the techniques that you have available, this is what you're trying to do, okay? So the question is, how are the features and thresholds selected, okay? So one simple way is, and this is just kind of just thinking about it logically, one simple way is to iteratively try different thresholds and then try predicting an output value with each regression tree model candidate, okay? For each predicted output for a given tree candidate, the approach compares the predicted value with the real value and selects the candidate that minimizes the error. So if we had a quantum computer, we could just run all possibilities and get the optimal value. Would you agree? You create all the candidates in the world, create all the possible thresholds in the world, all the possible outputs in the world, run them, compare them to the real values, and whoever gets the closest wins. Do you guys see that? And this is exactly how neural networks work, right? As well, except for the problem that we don't have a computer, quantum computer. So we're limited to CPUs and GPUs, and therefore the algorithm needs to efficiently, in an optimized way, needs to find the trees. Do you see that? So we can't just try all possible at once. So there's got to be an algorithm for the optimization. But in essence, this is what we're doing. Trying out candidates, trying out thresholds, trying out values in the leaves, predicting and comparing to the real value and minimizing the error. Questions? All right, so that's the general idea. And then the key question is how, the optimal algorithm that we choose. All right, and this kind of gives us the idea that we need to have a loss function. okay? And these trees are very interesting in the sense because they also have a loss function, like the loss functions that we have in neural networks, like MSE. You will see in the description that there is a J, for instance. But in neural networks, as you know, whenever you're training, you're calculating the gradients, right? We've done this before. We've talked a little bit about it, how we do the loss backward and step and all of that. And that's the point where we're deciding how we're going to update the weights, and we calculate a derivative. That's in neural networks. Regression trees work a little bit different, okay? Work a little bit different in the sense that we don't calculate the derivatives during training. You see that? So I want to make that contrast. So in neural networks, you calculate the derivatives during training because neural networks, have different architectures. In regression trees, you do not. You do have a loss function, but basically what happens is it's almost like you could say, if you were calculating the derivatives during training, they would always be the same. You see that? So basically, you only need to calculate them once, right? You define a loss function, you only need to do that calculation once, and then you basically derive general functions that you use. So when you're training a regression tree, you're just using like fixed equations. Whereas when you're training a neural network, you have to calculate the equations every time. Do you see that? You have to minimize the loss every time to update the weights. With a regression tree, you do not. And that might be something that's confusing, right? Because you see the loss function, so you intuitively assume that you would have to calculate gradients, but it doesn't work that way with regression trees. Do you guys see that contrast? Does that make sense? Any questions about that? So this is the one thing that was important for me to address with regression trees, okay? And this is stated in these notes. So the question is, how are the features and thresholds selected? One simple way is to iteratively try different thresholds and then try predicting an output value with each regression tree model candidate. For each predicted output for a given tree candidate, the approach compares the predicted value with the real value and selects the candidate that minimizes the errors. In the context of regression trees, and this is important, the difference between the real and the predicted values is called a residual, okay? So that's the other thing. It's got a specific name, but it's really this difference that you're always calculating, and you call it a residual. The loss function is very similar to the minimum squared errors MSE loss function. In this case, the objective goal is to minimize these errors, okay? All right. So given a set of output values in a node, for instance, each value will be tried iteratively, and the sum of the squares, residuals basically, will be calculated for all the threshold candidates. Once the optimized threshold is calculated, the process can be repeated by adding new nodes, okay? And so this is the process of increasing the trees. When a node can no longer be split, the process stops, and then it is called a leaf. And this is where you no longer have a decision point, but instead you've reached the leaf. Now you need to do a prediction. Huh?
So when it hits a leaf, it tries to hit the tree?
So that's actually a good question. So if you look down here, a tree is this. That's a tree. So it's basically, you start with a subtree, and then it's a linear sum of trees. You see that? So a regression tree is this whole thing here. And the algorithm first calculates one subtree, and then the next step, so for instance, let's say for XGBoost or AdaBoost, for the simplest example, AdaBoost, the first subtree just predicts the average. So all the y's calculate the average, that's that value. Do you see that? And then what do you do next? You're going to now create a new subtree that you're going to try out. And this subtree is, you start with a node, and then you're going to build it up, and it should predict some values. And these values basically get added to the original one, so with a learning rate. And you keep doing this process of creating new subtrees and subtrees until you arrive at one big tree. Do you see that? So it's a linear sum of subtrees, basically. Okay. And they're all and you have this idea of a learning rate. Okay, so this is kind of the overall description of a regression tree. We will come back to this next week just to kind of wrap up and look at all the individual ones. Okay, but hopefully that gives you a basic intuition of how one is built. Okay, so remember, you're creating a tree. The tree has decisions, which are the decision nodes. Then you have leaf nodes, which do the predictions, and that would be one, except that, and basically, as I said, you try different thresholds and different values, predict versus the real, and select the candidates that optimize, that are the best ones. And iteratively, you're going to just be adding individual trees. So you start with one, right? So think of this idea, right? So you start with this. What does that do? It just predicts the average. You guys see that? So if the average is always in the wine data was like 6, right? So it would always predict 6, but some values were 6, so you take that difference, and other values were 8 or 9 or whatever they were. You took those differences, right? And now you need to create another subtree, okay, of different nodes, different thresholds, different predicted values. And that subtree needs to predict the value that gets added to this value to make a new prediction, a better prediction, okay? And so that, once again, it's going to predict values that get compared to the real values. Do you see that? Now, one thing that you also do is that you're adding this learning rate, basically, so that you can decrease the impact that this subtree has on the overall value. And you just keep doing that iteratively until you find the best tree, basically. Okay? So let's it's 6:21. Let's leave it here for now, because this is a big topic, and then we will come back to it next week. Okay, so to wrap up regression trees, we will go over so we kind of got to here. We'll go over eta boost and just kind of how that works and how the subtrees are added. Then we're going to look at gradient boost, and then we're going to look at XG boost, and that should be the final one. Maybe we'll look at random forest. But are there any questions on the idea? So for now, just try to understand the idea of how it works. So again, what is it predicting? Why, right? So for instance, the wine quality. So wine quality is 7, the real value. This should predict 7, right? How does it do it? The first subtree predicts the average, 6, right? So 6 to 7, there's an error of 1, okay? So now you need to add another subtree. You need to select a set of features, right? It might be these 3 features or all 7 features, whatever it is. Build a tree to arrive at certain nodes and predict values. Those values times the learning rate get added to this. So now it's going to be, maybe, if this is, the real was 7, right? If this is 6, you would really want this to predict what? 1, and add it to that 6 to become 7, right? But you're iteratively doing that. And initially, this may not predict 1. This may be 6 plus 0.10, right? But it gives you, at least, what happens is before it was 6 and the real is 7. Now it's 6.10 and the real is 7. So the error has what? Decreased a little bit, right? To 0.90. Do you guys see that? So what do you do now? Okay, do another tree. And then the other tree with the same learning rate. Okay, 6 plus 0.10. And then maybe now you predict 0.20. So you have 6 plus 0.10 plus 0.20, 6.30. 7 is the real value. The error is 0.7. So it has decreased. And you keep doing that iteratively until you find the best tree. Yeah.
So you said having a lower learning rate makes the trees affect each other less?
So the learning rate usually is 0.01. I have it here.
Okay.
So so if you don't have a learning rate, the problem is the subtrees have too much impact on the value. So it's kind of like with learning rate in other neural network things where we, we want this to take a while, right? So we don't want it to jump so much. So we kind of incrementally change the weights. Here, what we're changing is the impact of the predicted value of this subtree that gets added to this other subtree. But as you can see, in the end, and I think I wrote it here. Where did I? Oh, yeah, here. So, you know, a tree is a linear combination of subtrees, basically. You can see that there. Okay, so this is the general idea of how these work. And then basically there are the specific algorithms that train them efficiently. Okay, so if we could try all of the subtree candidates in the world, right, and all the thresholds in the world and all the features in the world, and then compare them to the real value, we would be able to select the best one. But that would take forever, right? It's impossible and unfeasible. And so that's where you get all these different algorithms, such as XGBoost, random forest, etc., gradient boosting, which have their specific ways of doing the calculations. Does this idea make sense, guys? Any questions? If I asked you in the exam to explain, would you be able to say? Yeah, go ahead.
So the formula which is like just like.
Which formula? This one?
The subtrees and
this
like,
this one? Yeah.
So when we like are talking about a specific subtree, are we talking about like the same model we are using again and again?
Not necessarily. Each one can be its own subtree. So the algorithm is creating different subtrees of the data, but with the goal of giving a sample, right? So remember, to think of the wine quality. Our input is a vector of 11, right? That needs to go into this tree, and we need to get the quality rating of the wine, which was like 8 or 7. So that data goes into these subtrees. Now, this one, you might argue, has no input because all it does is it predicts the average, which we saw was 6. But the other ones will have, I mean, if you think about it in theory, subtree 1 could only have 3 features. Do you see what I'm saying? Because you're technically trying, I mean, that would be one of your candidates, right? So just 3 features with these thresholds of the sample, and that gives you a value. And that value gets added to this other subtree and so on. All right, until you build a subtree that's the best for predicting a value. Any questions? Make sense? All right, so this is just, as I said, a general idea, okay? And then we will come back to all these individual ones just to kind of contrast how they are. They all lead up to XGBoost, which is, as you can see here, if I click on 17, it takes me to this paper, as XGBoost, a scalable tree boosting system. And as you can see, this paper dates to 2016. So it's basically taking, it's the most recent one. So this is why I say that in theory, it should be better than random forest, because random forest has been around for a long time. Whereas this paper, 2016, proposed XGBoost, right? So I think just in the parameters, it's possible that if we had played with those parameters a little bit more, you could have gotten a little bit higher, right? And this is kind of what I mentioned. So maybe read through this paper if you're still interested in getting a better result on the homework. Although, I mean, you all did a great job. Yeah, go ahead. Well, so let me put it this way. It's a good question, right? Let's reason about that. Random forest, which is what gave us the best result, has been around for a while. This paper was published in 2016, XGBoost. It is like somebody is saying, hey, we just built a thing called XGBoost, and it's pretty good. So I would argue that it's possible that XGBoost, which is also a regression tree, just like random forest, could potentially be something to look at. I don't know because I would have to do the experiment, right? And I don't know that we can, but it's possible. That it certainly has more parameters and more things. We can you can look at the paper, for instance, which should be available. And this is kind of what I'm trying to show you in machine learning. It's how it is, right? You enter a competition, you got to look, okay, this is recent. We know how to use it because you already have the Python code, but drill down into the paper and find that little nugget of information that says, you know, what the depth of the tree should be, etc. When you guys did like depths of 7, right? What does that mean in terms of what we're doing here? It means that you're saying where here, right? Now in XGBoost, this is 0.5, by the way. So it's 0.5, but you're saying that this next subtree is 6. You're gonna build nodes of 6 levels. I think it was the optimal. I can't remember. Do you see that? Whereas I think by default it was 3. So when we were building this subtree, it only got as far as 3. You see what I'm saying? So there's an algorithm that, you know, starts adding these trees with the learning rate, etc. And in the end, it tries to obtain the best result. So that's really the idea. And so you play with these parameters to build the depth, etc. Okay. Anyway, we will come back to this. I don't plan to do any coding of this because it's too involved. And we really need to move on to classification, but I will come back just to touch on a few more of the details of how these regression trees work. Okay. I do want to show you and then I guess I'm kind of running late on the first half, but let's just finish this thought of the paper. XGBoost, a scalable tree boosting system. Should be this one. It's on Argvix. Download PDF. All right, so there it is, right? So 2016, as you can see, that's the paper. So you guys have code, but you know there's parameters. So you probably want to look through this paper to kind of figure out, okay, what are the parameters that they recommend? You see a lot of equations here, and you might be like, ooh, a lot of equations. But really, I mean, they're not really that bad if you think about what the equations are. We'll cover those in the next lecture, and you'll see it's just the MSE with a couple of thingies there that called regularization parameters, which are a little bit, you know, nice. But at the end of the day, this thing here that looks very like difficult to grasp is just MSE. And it's really the key to the whole equation, okay? And then this here is just these parameters. So I've addressed them in the document, and I will cover them again. Notice they kind of do the same. They started with, you know, how does it work? Gradient tree boosting historically. But we'll cover this. And then it starts showing you how it builds the trees, basically, okay? They have their own algorithms for basic things, okay? How they do it, all right? Anyway, we'll cover this in the next lecture, but my point is you can skip all of that. Just read the document I provided for you, and then read through the experiment and see if you find anything like what was the depth that they used? What was this parameter or that parameter? Did they recommend something that I can translate to my code to obtain better results? Okay, this is kind of how you would approach it. Or you would even go to Kaggle and look at papers there and find out how they did it. Does that make sense, guys? So this would be the process to follow. Okay. All right. So that's so that's basically the discussion for now on this topic. So I'm gonna stop the recording.